the end was that using the particle as an example of a quantum mechanical system with some dynamical variable which happens to be just the path taken by the particle. We said that the amplitude for a particle to go to an event x2 starting from an event x1. Remember that all events have 4 numbers associated with them, the time and the space, okay, but I will just denote them by symbol x2. This can be written as a sum over paths of an amplitude for the path, which we argued should have the structure exponential I over h cross times some quantity which I said is called action, it is just a name. This A depends on the path. So, for every path there is a rule which gives you a number. So, that rule we have not yet discovered, but once you have got that, then if you sum over this will give you the G. And once you have that, then the amplitude to find a particle at some point x2 is given by the amplitude for the particle to be originally at some point and then to propagate. So, the amplitude for it to propagate is just what we have written down here. In fact, it is called propagator G x2 x1 multiplied by psi at x1 and integrated over just the spatial coordinates. This I stressed even that day, and let me repeat it again. This x1 stands for t1 and the spatial coordinates x1. This stands for t1 spatial coordinates x1. This is t2 spatial coordinate x2. This is at time t2 position x2, but the integration is only over where it was originally at a given time t. Okay. So, given this is what we would have called wave function, and in fact, it will turn out to be the wave function. So, this wave function at a given time, if it is given, this amplitude tells you what the wave function at a later time is. It turns out that this itself is a very strong condition on the kind of dynamics you can have. We will explore it in detail in a moment. So, as far as this quantity is concerned, which contains all of the dynamics, once you know this, you know how this system evolves. So, there are 2 more comments which I wanted to make, which I had made in the previous lecture, but this is just to remind you. This is a very general formalism. Here x1 and x2 I am using as particles because it is at an introductory stage and I want to use ideas which you are familiar with, so that we are talking about the position. But the same thing works for an electromagnetic field. If I tell you what is the initial configuration of the electromagnetic field, classically it will evolve along a particular way to a final configuration. Quantum mechanically it can evolve in any way it likes. This is just like classically if I send an electron from one point to another point through slits, it will go along a specific path. But quantum mechanically it has an amplitude to go along any path. So, a path is better thought of as a history. So, the history of the system evolving from one time to another, and there is an amplitude for every one of those histories, and this action in the case of electromagnetic field will be a number which you can generate given a particular history. Then you sum over all the histories instead of summing over all paths, it is just a change in the nomenclature. Then you will get a propagator for the electromagnetic field. And then if you tell me what is the initial amplitude for a given, let us say, magnetic field configuration to exist, you will know what is the amplitude for a final magnetic field to exist. So, there is something like Schrodinger equation even for an electromagnetic field, and we will derive it at some stage, and from that we will see how things like photons come about and all that sort of stuff. Okay. So, this formalism is very general, but we will illustrate it in simple case of a particle moving from one point to another to begin with, and then we will proceed from that. And the second thing is that this is at this stage very formal. First of all, we do not know what A is, that is what we are going to concentrate on today, and the A depends on the system. For an electromagnetic field it is something, and for a particle it is something, and in fact A defines the system. The idea of the physics is to guess all possible A's for a different physical system. Second, we do not know how to sum and what to sum over. So, when I say sum over paths, what kinds of paths we should sum over is decided by actually this to some extent, we will come back to that. and then we need to know explicitly how to compute this. I mean, how do you sum over all the paths and get an answer, okay. So, all these we will take. Okay, so let us start with the first case, namely what is the A for a particle. Let us say, let us start with a free particle. So, if I have a free particle and it is going from one place to another, so what should this A depend on? So, what we are talking about is that you have again a space time diagram. This is space and this is time, and there is one event here and another event here, okay, and there is some path which is going from here to here. So, in this path we want to find a number which is capital A associated with this path, okay, and that number is called action, and that action is defined for every path. So, this path is given by some x of t. Here of course, it looks like t as a function of x, but this is how the path is defined. For a given x of t, I should be able to convert it into a number. So, I give you a function and you give me back a number, okay. Now, mathematicians and physicists also would like to call it a functional, very impressive, and you can tell people you are doing something with functional, but it is no more sophisticated than area under a curve. Suppose I have this curve. Now, think of it as y and x, y is equal to some function of x, and if I want to compute the area under between this and this, that depends on what function I am giving. If you give various functions, I will give you various areas between the same 2 points. So, you give me a function and I give you a number, that number is the area, okay. So, area is the simplest thing which you are all familiar with, but they might not have called it a functional when you learn calculus area under a curve, but area is a functional. So, the mathematical statement is that it is a mapping from functions to numbers. What is a function in general? Function, if you have y is equal to f of x, it is a rule which gives you one number when you give one number. You tell me what x is, then f at that value of x is another number. So, functions return numbers when you feed in a number, functionals return a number when you feed in an entire function. That is the only difference, but as I said, these are all just terminology, this has nothing to do with physics. So, let us leave that aside, but that is the terminology which one uses. So, action is called a functional of this path. Now, we want to find this amplitude to go from x1 to x2 by this rule, and we want to guess what this action is, what is the most reasonable thing for the action to be. Now, one thing which we can do is to divide this path into small bits, okay. Then what happens is that the amplitude for the particle to go along this particular path, which is what we are trying to find out, which is e to the I a over h cross. So, this I can also write as sum over paths of the amplitude for a path. This is how we started with, and then we said that this a of path is in this form. So, we want the amplitude for the path. So, the amplitude for the path is the amplitude for it to go from here to here, then here to here, here to here, here to here, right. But the amplitude will be multiplicative, because the amplitude to go along this is the amplitude for this into amplitude into this and amplitude into this, etc. It is just like the other rule. So, you multiply the amplitudes, but it comes in the exponential. So, this should be additive, that is, if I take a small bit of path and then if you keep multiplying this, then that is going to get added up, or rather if I write this a as a for one small bit, a for another bit, a for another bit, etc., and I multiply all of them together, the a for the whole path will be the addition of bits for these paths. So, I want some quantity constructed from the path which is linear and additive in the length of the path. Now, what is the simplest object? Simplest object is length itself. So, the simplest thing which one can think of is that this action should be proportional. So, I will put some constant k times, okay, it actually turns out to be more convenient to call it minus k. This is just because of notational convenience later on to connect up with what we know, times the length of the path between the two events x2 and x1. Now, I said this is the simplest one. There is one more possibility which exists, which will come up later on, but let us first go with this, okay, then I will tell you what is the other one. So, what one is actually saying is that dA is dl. So, if you take a small length here, that contributes an amount dA which is constant times dl. So, if I keep multiplying all of them, since there is an exponential I over h cross of dA and you are multiplying this, they are all going to add up and it will give you the total length. So, the total amplitude is going to be equal to this, proportional to this length k between the two events. So, I have a path like this and I want to define the length for this path. Now, we are stuck, we cannot do it. This is the whole problem in working with approximate theories. If you are working with non-relativistic quantum mechanics, which is what Schrodinger equation and everything is about, and you want to find out what is this A which will generate the non-relativistic quantum mechanics, you cannot do it. You have to come up and give an extra rule. And as I said, my aim in this course is to try to avoid giving extra rules, and I want to derive everything from one principle. Non-relativistic quantum mechanics is an approximation, because non-relativistic classical physics is an approximation to relativistic physics. So, in non-relativistic physics, there is no such thing as the length of a path in space time. Of course, there is length of path in space. So, if I take a path, I throw a ball and it goes and hits the wall, and if you want to know the length of the path it is taken, of course you can measure it, but that is in space, but that is not in space time. What we need here, this path is not in space. In space I can just project it. If it is 2 dimension, it will follow some curve. What I need here is a length in space time. So, a length in space time does not exist in a natural way in non-relativistic mechanics. Therefore, in order to get non-relativistic quantum mechanics, you have to start with a relativistic physics and then take an appropriate limit. So, exact theories are often more beautiful, requires less assumptions and more natural. Okay? So, there is no concept of length of a path in non-relativistic physics, but there is a length of a path which is in special relativity. So, I want to write that down for you. I am sure some of you must have seen it, but otherwise I will just explain it briefly. The length of a path in a space time is denoted, the square of the length is denoted by ds square, and it is taken to be minus c square dt square plus dx square. This will be derived somewhere along the line in your graduate course, but I am assuming that all of you would have done this in MSc level in some form or the other. It might not have been emphasized, we are going to emphasize it quite a bit. What it is that in normal physics, normal everyday non-relativistic physics, dx square, which stands for dx square plus dy square plus dz square, is the infinitesimal length of the path, square of the length of the path. You take a square root and you get the length. Relativity adds to it c dt square, which is in the time dimension, but it comes with a minus sign. That minus sign is crucial, but that is the way it works. So, I am not going to work this through, I am going to assume that you have seen it somewhere, otherwise you need to look it up, okay, or talk to me or Karthik or something. Okay. So, this is the length of the path. Now, of course, to be very precise, this ds square has a couple of more important connotations which I wanted to tell you. One is I have put minus here. You could have put this plus and this as minus, it does not really make any difference, and I would use this. With this notation, minus ds square is essentially the time if the particle is not moving. Suppose the particle is not moving, suppose you take a path and the path is such that the x does not change. You can also have a path in space time where a particle is simply sitting somewhere, this vertical axis. It is that x is equal to 0 all the time. Okay. So, it goes in time, but it is not moving in space. So, if I put dx is equal to 0, then minus ds square except for c factors etc. tells you the time shown by that clock. So, if I have a clock which is sitting quietly at some place, then this is the time shown by that path. Okay. And if it is moving, what happens is the following: you can take minus c square dt square outside and you will get 1 minus v square by c square. so I am pulling c square dt square outside, that will give you a minus sign here. The first term is this. In after the minus sign, I have a v square. What is v square? V is dx by dt. So this c and this c cancels. Dx square by dt square multiplied by dt square will give you this. So if the particle is actually moving with a velocity v, then this quantity still measures the time. Take away this minus and take away this c, it measures the time, but now the time is smaller. It is smaller by the factor 1 minus v square by c square. So when you take dt, you will put a square root, and this is the so called time dilation effect in special relativity. I mean, you can derive it at one step from this. So for any particular particle moving along a given trajectory, this ds square has the physical meaning as essentially the time, but for the sign minus sign and a c factor, it essentially measures the time shown by a clock which is moving along that path. Okay? It is also the length of the path in this notation. All right? So we do have a notion of a length of a path, and we do have a way of writing this action now. So this action in this can be taken from integrating this to get the length. So what will be the integrated length? So if I want to take the length, it is ds with a extra minus sign, because I don't want this minus sign to hang around. That is why many people use c square dt square minus dx square, but I thought it is nicer to have an idea where your dx square, the spatial part, comes with positive sign, and whatever is extra in relativity with time, that comes with a minus sign. Okay? So don't worry about the minus sign. If it bothers you, you just flip that. Okay, so what will be the length? So the length is going to be integral of dl. dl is same as ds with a minus sign. So it is going to be integral c dt into square root of I will put it as half. So square root of 1 minus v square by c square to the power half. Just to make it absolutely clear, I will replace v square by x dot square. V is x dot, so this is x dot square. So let us think about it for a minute. So this is what the action is going to be. The action is just proportional to length, except for a constant. This is what action is going to be. So what does it tell you? It tells you that you give me a path x of t, which I have shown here. You take any path you like, which connects these 2 points. Then for every path, you compute this integral. So given a path, you know what is x dot square, you can plug this in, take the square root, then you can do this integral. And once you do this integral, you will get a length L. Therefore, you know the action. So the action will be a number. So for every path, you get a number, and that is what I said a functional does. You give me a function which is x of t, then I give you a number which is obtained by this integral. Okay? So this, given this L, if I go and write down the expression for A, that is going to be minus k or A over h cross, which is what is going to appear here, minus k over h cross integral over dt of 1 minus x dot square by c square to the power half and a c. That c comes from this c dt, c. Okay? So you have something like this, and you can see that this is dimensionless. So this should have dimensions of angular momentum. So this entire concept, if you are going to take it as c dt as the length, then you need to get some object which has the dimensions. Suppose you think of this as time. Then the h cross has dimensions arc second, which is the angular momentum dimension. So second is taken care of here. So this should have the dimensions of energy. and the only quantity you have for a free particle is a mass. And you have, of course, we have introduced special relativity, so there is C. So, if K is proportional to mc, you can get an mc square here. But why do I want mc square? Why not 13 times mc square? Sure, you can. But the point is that this is what defines the mass of the system. So, I told you that the action defines the system. So, you say that the action for a free particle is integral dt 1 minus x dot square upon c square to the power half times a constant, and that constant multiplied by h cross divided by c square defines a property of that particle, and that particle's property we call mass. Okay. So, you do not have to introduce mass in any other funny way, it is just a definition. It is a parameter which appears in the action, and later on when we do electromagnetism we will find that there is another parameter which appears in the action which is called the electric charge. So, these are quantities which come up through the action, and from the action you can obtain all this. So, you have got this expression, and with this expression you can go ahead and compute everything. Okay. Now, I am going to do this in a minute, but before we do that, there is a comment which I wanted to make. I mean, here of course it is just a free particle. Okay, it is a particle which is moving with nothing affecting it, and therefore I could just calculate this length and put this here. Now, can we do better? Can we do a situation where something non-trivial is happening? Yes, you can. You can, for example, describe a particle in a weak gravitational field. Now, the reason is that if there is a weak gravitational field, there is again a definition for a length in this spacetime. Okay. So, here we wrote the length in the spacetime by this minus c square dt square plus dx square. It turns out, I am going to prove it in a minute, but let me just first write down the answer. The answer is that 1 plus twice the gravitational potential upon c square times c square dt square plus dx square. This is the length in the presence of a gravitational field. That is, here we had a formula for a particle, just an isolated particle. You just take this dt square and you multiply it by a factor 1 plus 2 phi by c square, where phi is the Newtonian gravitational potential. Remember that Newtonian gravitational potentials has dimensions of square of the velocity. Remember, escape velocity v square is gm by r. Gm by r is the gravitational potential. Okay. So, this phi has dimensions of c square, so this is a dimensionless factor, it gets added. Now, suppose this is true. If this is true, we can play exactly the same game and define the length for a particle in a gravitational field. Now, it turns out that this works because gravitational field is not a field and it is just curvature of the space time, and the what you call geometrical distance between 2 points or the time interval between 2 events changes in the presence of gravitational field, as a result of which in the weak field limit of Einstein's theory, this is what you get. So, again exact theories are very nice, and you can put this in and you can find what is the action for a particle in a gravitational field. That is all we will need for a moment, and then we can do a lot of things with those two, and then we will come back to more general system. But I have to prove you this. Why is it that if I have a gravitational field present, the distance between two events changes by this? Now, nothing is happening here. So, all that I have to prove is the following. Suppose there is a particle which is sitting quietly on the table, okay? And better still you attach a clock to it, or better still you put a clock on the table. You put a clock on the table, then this relation tells you that when dx is equal to 0, ds square actually measures the time shown by the clock, right? Now, suppose the particle is actually moving, then the time shown by the clock is given by this. This is the time dilation effect. So, if I have one clock at rest and another clock which is moving, no gravitational field yet, and another clock which is moving, the moving clock will slow down. Correspondingly, what this result tells you is the following. If I have a particle at rest in a gravitational field, think of a clock which is kept here, and now take Earth's gravitational field into account. Earth's gravitational field becomes weaker and weaker. At infinity we take phi to be 0, and at any given point the phi is negative, right, minus gm by r. So, this phi, so this is not there because the particle is not moving, so dx is 0. It tells you that the time shown by the clock gets modified by this factor, where this phi is something like minus gm by r multiplying it, minus 2 gm by r c square is what you will get, which means that it is slower compared to a clock at infinity, or compared to a clock which is not experiencing a gravitational field. So, what special relativity tells you is that if you have two clocks, one moving with respect to the other, then that clock slows down. In what general relativity tells you is that it need not even move. If I have one clock on the top of the table and another clock at the clock at the bottom slows down compared to the clock at the top, because the bottom is at a deeper gravitational potential. So, phi will be larger, modulus of phi will be larger, with a negative sign it will slow down more. So, what I have to do in order to prove this is to show that if I have a clock which is kept in a gravitational field, time changes like this. Okay? This is what I am going to do next. It turns out that it is fairly easy, and it uses a concept called principle of equivalence, which was one of the greatest things which Einstein did, in the sense that he understood its meaning and its importance. So, let me just introduce you to the principle of equivalence and derive that result. What principle of equivalence tells you is that there are two kinds of masses one can define, called inertial mass and gravitational mass, and these two are equal. So, let me explain what it means. So, suppose you are doing electromagnetism for a moment. So, in electromagnetism, the equation of motion for, think of electrostatic, just an electric field. So, mass into acceleration you will write is equal to q times the electric field. If there is a charged particle in an electric field, q times E is the force acting on that charged particle, mass times acceleration is equal to this. Now, suppose instead of electric field there is a gravitational field. Okay? Then what you will do is you will write another equation which says mass times acceleration is equal to the force, which you will now say is mg, right. But to be precise, I should call this the electric charge, and I should put a gravitational charge here. Think about it. See, mass into acceleration is always the left hand side of Newton's equation. On the right hand side you have to tell me the force. Now, the force in electric field is a charge, electric charge times the electric field. So, force in the gravitational field should be the gravitational charge times the gravitational field. That is the most logical thing to happen. Why should this gravitational charge be numerically equal to the inertial mass here? In the case of electromagnetism, they were not equal. There is a q by m. There are particles with 0 charge, there are particles with negative charge, particles with positive charge. Nothing of that kind happens in the case of gravity. There is no negative gravitational mass, positive gravitational mass, 0 gravitational mass, etc. It is always equal to this m. Okay? Now, this was known from the days of Galileo. I mean, this is why I can cancel these two, and then the acceleration in that gravitational field is the same for all bodies. If I take a 5 kilogram body and a 1 kilogram body and I drop it, they both will hit the ground at the same time. But if I take two different masses and put it in the same electric field, and if they have same charge, they will move with different acceleration. Okay? So, here the acceleration is universal, here the acceleration is not. That is because this is equal to m, and you can cancel out these two m. Okay? Now, Einstein realized that this immediately tells you that space time is curved. Now, that is part of general relativity, so I am not going to go into it, but I will just extract from it what we need. What we need is the following. Suppose you compare two situations. One situation where there is a box which is near Earth, and then the second case is a box which is going upwards with an acceleration g. So, think of some rocket attached to it. So, that this is in interstellar space, it is a spaceship, the same box as this, and it is going up with an acceleration g. here this is a box which is sitting next to earth and it is going down. There is the box is not going down, but things there are feeling this acceleration g. Now think of two bodies, let us say one large body and a small body, and you drop them. Because this m and m get cancelled out, in this g both of them will fall down with the same acceleration, they will hit the floor at the same time. Now let us do the same experiment here. You have this large body and you have a small body and you let go. There is no force acting on them, so it is not going to move, it will just stay put there. But the floor of the rocket ship will come and hit it at some time. But the floor of the rocket ship does not know anything about these particles or their masses. So it has to hit it simultaneously. So the fact that this is one of the deepest principles and most beautiful principles in physics. The fact that these two bodies fall down and hit the floor at the same time says that there is an equivalence between these two. That whatever is going on in a box near Earth's gravitational field can be mimicked by a rocket ship which is going upwards with the same acceleration. Okay. Now this is called principle of equivalence. Again, I do not have time to discuss it in greater detail, but I am just going to use this for something which we need in order to derive that. Now we will, the principle of equivalence in the broadest form says that any physical phenomena in this local region is going to be the same as the physical phenomena in this. So for example, the way clocks will behave here and clocks will behave here are identical. But that is good. How clocks will behave here we know. Accelerated frames can be completely studied in special relativity. Only when gravity comes in you need general relativity. So this is an accelerated frame with a clock and that clock is going to move. So if I attach a clock to the wall, then the clock is going to move and I know how to study moving clocks. So since I know how the clock is moving and how it affects its rate, I can figure out how it affects this rate, which is what we are going to do. So let me just finish, this is almost obvious now, so but let me finish this off in a natural way. What you are going to do is to say that this is equivalent to this, which means that in Earth's gravitational field, if I have a freely falling frame, suppose you are in the lift and somebody cuts the rope of the lift and the lift is falling down, then you will feel weightless. This is Resnick and Halliday, you would have studied it and all kinds of things, spring balances in a lift which is going up with acceleration, coming down with acceleration and all that. If it is freely falling, you do not see the effects of gravity, which is exactly the same as this in reverse, that if there is a gravitational field, you can neutralize it by going to a suitable accelerated frame, which is like a freely falling frame. So in a freely falling frame, there is no gravitational field, and if there is no gravitational field, I can use special relativity. So in the absence of gravity, I can use special relativity, then I can translate it to the other frame. So how do you do this? I mean, there are several ways of doing it. One practical way of doing this would be this: take this wall and you put clocks there. Okay, this is, think of this wall and you have fixed clocks there. So these are reference clocks, say A, B, C, etc. These are in a gravitational field, there is a wall in the room, so there is a gravity acting downwards, some G, or rather there is a gravitational potential at all points. This potential we normalize to 0 at infinity, so there is a negative value at these things. Now what I am going to do is to take another clock which I let it drop in this frame. So you have these clocks in the wall and another clock is dropping down. Now if I am sitting on this dropping clock, then I can use special relativity there because I do not feel any gravity. What will I see? I am going to see in the frame in which this clock is at rest, I am going to see this going up, this going up, this going up, right? And I am using special relativity now because I do not feel any gravity and I do not know why it is going up, but it is moving up. So I can use special relativity to compare the rate of this with rate of this. And I know exactly what it is. See, the rate of a clock in the gravitational field phi, which is this clock, but I know what it is because it is moving up with a velocity. So this is the rate which I am going to measure, which is, let me call it freely falling or inertial clock. So I will put it I. This is the time I measure into 1 minus v square by c square, where v is the velocity with which it is moving up. What is the velocity with which it is moving up? That is same as the velocity with which I was coming down, and the velocity with which I was coming down, I have put my reference point at infinity. So, at infinity I was at rest and I was freely falling. So, energy conservation tells me that half v square plus phi should be equal to 0, because at infinity I had 0 velocity and 0 gravitational potential. Therefore, v square is equal to minus 2 phi. So, you plug minus 2 phi here, that is it. So, the clock rate in a gravitational field phi will be the clock rate in an inertial frame, that is the one which has no gravitational field. So, I can say phi is equal to 0 times 1 plus 2 phi by c square. This is exactly what we have got here. Once I have the time changed by this, then I can multiply by c square and everything will work. Okay? You understood this argument. Okay. Yeah. All right. So, you got up to 1 minus v square by c square. Okay. Now, we want to know what is the velocity. What is the velocity with which this B clock is moving up when I see it from this frame, in which special relativity is valid, and I can use 1 minus v square by c square relation, which is a relation from special relativity. So, I want to know what is its velocity. It got this velocity because I was freely falling and I went to my rest frame. So, I want to know what is the velocity with which I was freely falling. The velocity with which I was freely falling is standard classical mechanics question. So, my energy is conserved. So, the half mv square plus m phi, m is cancelled out, and that quantity should be equal to the energy at infinity, because I am falling from infinity. At infinity phi is 0 and I was just dropped at infinity. So, v is 0. So, this thing is 0. Therefore, phi is equal to minus 2 v square. I mean minus 2 phi is equal to v square, that is what I substituted here. Okay, fine. So, we have this result, therefore, we have this result. Now, let us redo this calculation and compute what is the length. Okay. Now, all this is valid only in weak gravitational field, and in fact, we want to do non-relativistic quantum mechanics. The only thing I did all this is because if I am doing just non-relativistic quantum mechanics, I cannot tell you what is the action. I had to postulate, and I do not like postulates, I mean unnecessary postulates. So, you can derive this once you start with a more exact theory and you derive this as an approximation. The approximate theory is know where it came from, and as a result of which we know the more exact theory. Okay? So, that is why I followed this route, but after this we will take the non-relativistic limit. So, let us look at this, and what will be the L here? So, the L is going to be same analysis as this. L is going to be integral, okay, let me do it in step by step. So, this quantity, and it is going to be integral over dl. So, dl I had to flip the sign and then take a square root. So, it will be c dt, then I will have 1 plus 2 phi by c square. Then I will pick up from here, I have flipped the sign. So, it is a minus v square by c square, the whole thing to the power half. Okay. It is exactly the same as this, except for minus v square by c square, you also get this 2 phi by c square. Because we are looking at a weak field, this square root, c is very large, we are looking at non-relativistic limit. So, this square root can be approximated by a factor half. So, this is half and this is minus half v square, and I will put an approximation sign here. Okay. So, you have this, and you are going to get first a c dt, that will be c into t2 minus t1. I can integrate that quantity, c dt between 2 points 1 and 2, that is c d2 minus t1. Then you take this rest of it. Okay. Actually, at this stage it is also more convenient to take this minus kl, and that k is minus mc. So, let me at least put a minus sign, that will make life a little easier later on. So, I put a minus sign here, this is minus, and then this quantity I am going to take the rest of it with the minus sign. So, that minus sign acts on this and it gives me plus half v square by c square, then minus phi by c square. This is coming from the second term, these two times a factor c, right. So, if I go and write down this action now, I could have done exactly this thing with the action, then what I will find is that I have to multiply this by mc square by h cross, and what was replaced here is that this dt, which was 1 minus x dot square by x square, is now going to pick up this plus phi by c square from this 2 phi by c square with a square root. So, let me do that also for you. This is just to tell you that the length gets modified in some form, and let us do the same thing with the action. So, if I do it for the action, then what I will get is that a by h cross will be minus mc square by h cross integral dt. This is 1 minus v is same as x dot. So, v square by c square, and what is going to happen is that you are going to pick up a plus 2 phi by c square, and then there is a square root, correct. So, this I approximate by taking this 2 inside and taking off this 2 and removing this. So, that becomes approximate, but we will see it is a non-relativistic action. So, now this is going to become again minus mc square by h cross T2 minus T1 is the first term. Then I will have minus mc square by h cross integral over dt in the second term. So, I am going to flip the sign, so that in the second term I have a half v square by c square, that c square cancels with this, and then I have a phi by c square cancels with this. So, this is what you get. Okay. So, let us stare at this, and in fact, in order to stare at it nicely, I will even remove this h cross, that is to make it dimensionless, but if I remove h cross, this is what I get. So, we have actually found for you, let me just draw a line here, we have actually found for you what is the action for a particle in a gravitational field. What is it? It has some quantity here which is independent of the path, it only depends on the endpoints. So, that is not going to contribute when we do anything with the path. Suppose I sum over all paths, this is always a constant. So, it is e to the in this it is going to appear as I over h cross times this. This is just a phase. Okay. I will have more comments to make about it a little later, but as far as our calculations go, this is irrelevant. So, what we have for the action is something which is integral dt of mv square by 2 minus m phi. Okay. So, people before us has called this kinetic energy and this potential energy. So, what we have as the action is an integral over dt of a quantity which is kinetic energy minus potential energy. Okay. And this quantity which is integrated over dt, this expression is usually called the Lagrangian. That is, you write this as integral dt times a quantity L, and this L in general depends on x dot and x and on time. This V is x dot square. So, in fact, more precisely I think explicitly I should write it as x dot square. This phi can depend on time and position, because it is the gravitational external gravitational potential. It can vary with time and it will vary with place. So, in general this L will depend on x, x dot and t, okay, and the action will be an integral of that over time, and this is what we get. So, in this approach you actually derive what is the action for a particle in a gravitational field. In order to do that, just let me run over the logic. The only assumption we actually made, I mean assumption in the sense of something very non-trivial. Of course, all along there are various hidden assumptions, but the really non-trivial thing is the two-slit experiment, from which we argued that the amplitude for a from which we first argued that there has to be an amplitude, and the amplitude for a particle to go from event to event is the sum over these paths. Then we argued that this path should have this form. Then we argued that if we are talking about a single particle, not free, a single particle which is moving along the path, then it is natural to use some element which is linear in the length for the action. So, we took this action to be this times length. As I said, there is just one more possibility there which I have not discussed, which I will come back to. So, this is the length, and then all that I needed was the length of a path in space time. At that stage everything broke down, because there is no such thing as a length of a path in space time in non-relativistic physics. It just does not exist. There is a length of the path in space, but there is no length of the path in space. So, we have to say that, oh, non-relativistic physics is an approximation, can relativity do better? And relativity actually does better. In special relativity there is a length of the path from which we can obtain this result, which is just a special case of with the gravitational field. Okay. So, you can obtain this result, and we can actually write down a Lagrangian or an action for a special relativistic particle. Then we said, can we do better? And we said, yes, we can, because if you go to general relativity, there is a definition of length of a path in space time in general relativity, which in the weak gravitational field is just 1 plus 2 phi by c square multiplying this. And because of which I can again play the same game and find what is the action for a particle in a gravitational field. Then we find that the action for a particle in a gravitational field is integration over a Lagrangian, and that Lagrangian happens to be kinetic energy minus potential. So, I do not have to postulate anything, okay. Everything comes out of this logic. Now, very often people say that Lagrangians are kinetic energy minus potential energy in general, and this statement is simply wrong. Okay. In fact, Lagrangian is not kinetic energy minus potential energy for any exact system in the universe. As an approximate system, it is valid definitely for a particle in a weak gravitational field, as we have derived. It is also valid for a particle in an electrostatic field. Suppose you have an electrostatic field, then instead of this gravitational potential you can put q times the electrostatic potential and it will be valid. It is not valid for a particle in a magnetic field. If you take a particle in a magnetic field, the standard electrodynamics, there is no relativity or any fancy business. If you just take a particle in a magnetic field, you cannot write down the Lagrangian as some kinetic energy minus some potential energy. It just does not exist. Okay. So, if you find some discussion why kinetic energy minus potential energy is important, etc., that is a misplaced discussion, because that expression has no serious meaning. It just happens to be that in an approximate limit. Okay. Fine. Now, we want to go further and work out all its consequences, which I am going to do now. But before we do that, I want to make one comment. I kept saying that there is one more example, and that is all there is. If you want to have a particle which is influenced by an external field, it can be influenced by gravity or it can be influenced by electromagnetism. We haven't covered electromagnetism yet. So, what happens in the presence of electromagnetism? In the presence of electromagnetism, the length does not change. See, general relativity applies only to gravity. There is no geometric description of electromagnetism. So, it is not that the length changes. But when I said that it has to be linear and additive in length, I did not take into account all the possibilities. There is one more possibility which is left. So, let me just try to illustrate that. So, to do that, let us go back to this expression for ds square which we wrote down here. Okay, and I will use this space. Now, in this, what is this dx square? Dx square can be thought of as dx dot product with dx, right. So, it is just 2 vectors, you take a dot product. So, I would like to write this whole thing as a dot product. So, obviously, the vector now should have one component with one spatial component which is dx dy dz. It should have a time component which is c dt. Then I have to take a dot product. Okay. But normally when you take a dot product, you take the component by component and add them up. So, we will introduce a rule, it is just a mathematical definition, that the dot product in space time is taken with positive signs for this, with a minus sign for this. Then I can write this down formally as something like dx. I need to invent a notation here. So, I will put 2 lines, dot dx. You will not find it in other textbooks, this is just a temporary notation for this class. Okay. So, if I had just put a tilde there, that is a 3 vector. If I put 2 lines, think of it as a 4 vector. So, that vector has 4 components, it has dx, dy, dz, it also has a c dt, and the dot product is done with the rule that this minus dt square is put, that is all. Now, you find that this is not linear in dx, it is quadratic in dx, but when you want to get the length, you took a square root, then you got something linear and we played this game. Okay. But you can do something else, you can have a quantity which is some vector. Let me call that vector, okay, it should not confuse with action, but let me call that vector A. In 3 dimension, I could have taken a vector A and I could have taken a dot product with dx, these are 3 dimensional quantities, and that is linear in dx and it is additive in dx. So, if somebody gives me a vector like this, I can construct this quantity. Okay. But I want it in 4 dimension because this is in space. Remember that we want lengths in space time and everything should be in space time. So, I can generalize this into something which I will call A 2 lines dotted with dx 2 lines, right. Now, what does that mean? This is dx dy dz multiplied by ax, ay, az, that part is fine. Then I should have a minus sign, then this has c dt and there should be some other component here, that 4th component we will call a0. Okay. So, roughly speaking, this is not roughly, I mean with this definition precisely, it will have the form something like a0 dt plus a dot dx. Okay. So, instead of this a dot dx, we just added to it an extra bit, just as this dx by this thing we added this in the square roots with the square root finally, you can do this. So, you have 4 quantities here, there is a 3 vector with the 4th component added, that is called a 4 vector. So, if I have a 4 vector A, then I can construct one more term in the action, then I can do an integral of this and that will be a part of the action. If you do that, you get electromagnetism. So, I will derive this towards the end of the course. Okay. So, that will give you entire electromagnetism. This 3 vector A happens to be the vector potential, curl of it will give you the magnetic field. This happens to be the electrostatic potential, and in electrostatic gradient of that would have given you the electric field. So, there is one more possibility of getting the length, and that will be the integral over a object like this a dot dx in 4 dimension. But as I said, we are not going to do this at this stage, and I just wanted to mention to you that both gravity and electromagnetism can come by the same method. And what you have here is a full-fledged formalism for discussing how the particles are moving in it. And in fact, if you take for the length, the correct expression for a length in a gravitational field, what you get is a full theory of particles moving in a given in a black hole space-time or something like that. So, the approach is completely general. Fine, yeah.
Where exactly did you take the wind field in the A square?
In up to this point is fine. Then when I took this d, or let us look at it here. So, when I took the square root, I am taking C going to infinity limit. That is where I took the weak field limit. Yeah. Okay. So now we have got all this. Let us see what is it good for. Okay. So I want to define various formal objects and then we will proceed to calculate its implications. What we have essentially found, what can I rub? Okay, I can rub this. What we have essentially found is that the key object which we need is something called action, which is an integral over dt of some quantity which we call Lagrangian, which in general depends on x dot, it depends on x, and it can also depend on t. Most of the time we will ignore the t dependence, and it really does not matter, but whatever I have to say works even with or without t dependence. So, for simplicity I will just think of it as a function of these two. Okay. Now, we also found in the earlier lecture that this whole idea of writing it like this is that if I do delta of this A with respect to the path or history and you equate it to 0, that path is going to be singled out. So, the classical physics will come from that path. So, we already know how to do classical physics. So, we started from quantum physics, we discovered something called an action, and from that action we know how to do classical physics. So, we want to see what that equation implies for this. That is quite easy, but I need this for various purposes, so I will derive it for you. So, what I want to do is to vary the path and ask what is the variation of A. Now, it is important for you to understand what I mean by varying a path. What is meant is the following: you have x and you have t and you have two endpoints 1 and 2, and I have some path, and for that path I have a number 13.6. Then you change that path slightly, but keep the endpoints fixed. So, at any given point or at any given time, this path varies by some amount from the original one to this one. There is a slight displacement. So, you change that. So, what is done mathematically is to take this x and then change it into x plus some epsilon times delta x, where this delta x is some function. So, you take any function you like, sin h of t, and then you multiply it by an epsilon and add to whatever is the original thing, but just make sure this function is such that it vanishes at these two ends. Okay? So, the endpoints are fixed and then you add to it. Later on we will even think of a situation where the endpoints are varied. So, both kind of variations we will study. So, you do this and you want to know how this is changing. So, if I take a path like this and plug it in, then you are going to get the action as a function of epsilon. So, if you want to say that it should not change when I change the path slightly, the ordinary derivative of that with respect to epsilon should be 0. That is how you take this, that is how you give meaning to this relation. But actually you do not have to be that fancy, you can just do a delta and everything will work out fine. So, if you do this delta, then you have dt, and what you have is dl by dx dotted with delta x, then plus dl by dx dot dotted with the delta x dot. Okay. What is delta x dot? Delta of x dot will be, x dot will change by this thing and there is a delta operating on it, these two commute. So, therefore, I can write delta of x dot as d by dt of delta x, that is delta and the d by dt commutes, and this is what I am going to do. Now, I am going to rewrite this term in a particular way. I am going to write this as d by dt of dl by dx dot dotted with delta x minus delta x dotted with d by dt of dl by dx dot. Let us see what has been done. So, this is dl by dx dot d by dt of some quantity. So, I am taking this d by dt out of it. So, I take d by dt of this whole thing. So, I will have one term which is this d by dt of delta x, which is this, but there will be an additional term. That additional term will be delta x multiplying d by dt of this, which I am subtracting out. Okay. So, I can always write this second term here in this form. So, then your delta A becomes, there are now two terms. There is one term which is this comes with a plus sign and it is integrated over dt. It is a derivative of some quantity integrated over time. So, it is only going to give you this quantity at the endpoints. Just for convenience, I will introduce one more definition. I will call P the quantity dl by dx dot. It is just a definition. So, what you will get is this quantity is just P. So, you get P dot delta x evaluated at the endpoints 1 and 2, that comes from this. Then take the rest of the terms. Rest of the terms will be integral over dt. There is a delta x dotted with this delta x dotted with dl by dx, which is this. This delta x is out. So, it is d by dt of dl by dx dot, which I have called P. This is what you have for delta A. So, this is completely general. So, if I vary the path, this is what will happen. I have not assumed that the delta x vanishes at the end point. Now, there are two kinds of variations which one would like to study for this, because both of them are going to be useful for us. The first variation is that what is shown in the picture here. I am going to assume the endpoints are fixed. So, I am just going to think of all the paths which connect these two, which is what we did when we calculated the propagator. So, you have all the paths and we wrote down a form like this. Then we said that when you are varying the path which is going to contribute and stick out is the path which satisfies this, but with the endpoints fixed. So, if I take the endpoints to be fixed, delta x is 0 at the endpoints, because all the paths have the same x. So, this term goes out. Then when endpoints are fixed, the rule, this quantity, implies that this should vanish, and in between delta x is arbitrary. So, this term has to vanish. So, you get dp by dt should be equal to dl by dx. Okay. There is one more comment I want to make about the notation. When I varied and everything, I took dl by dx and delta x. So, dl by dx I am differentiating a scalar quantity with respect to a vector quantity. What you get is a vector. Now, if you did not think about it, which I am sure you did not, then everything will work out fine. Okay? If you stop and think, then you will wonder what do you mean by differentiating with respect to a vector, etc., etc. So, the idea is to do it without thinking. It will work out properly when you put all the components, etc. But you can think of it as Cartesian components if it bothers you. With Cartesian components it is perfectly fine. Otherwise, this should have been like gradient, etc. That just makes the notation clumsy. Okay? So, this idea will work, and this is your final this thing. So, this dl by dx is actually gradient of Lagrangian, that is what it means. So, if the Lagrangian has this form, what will you get? What is your P? P is dl by dx dot. So, this is m by 2 x dot square. So, P is just m x dot, that is the momentum. That is why I used the symbol P. Then, so dp by dt is the rate of change of momentum, and that is going to be dl by dx. What is dl by dx? dl by dx will come only from phi, and you will get minus m gradient of phi, that is the gravitational force. So, we already know that this entire formalism is consistent. I mean, whatever we have written down does give you what we know from Newton's law to be the correct equation in the presence of a gravitational field. So, that part is fine. Now, there is also one more thing which you can do with this, which is to go and calculate how this quantity changes when I just change the endpoint. Okay. So, what do I mean by that? What I mean is that I can have a path for which I have the action and I can vary the path, and I have kept the endpoints fixed when I varied this path. But I can do something else. I can say that I am only going to calculate this action for a path which satisfies this condition. That is, you take this, a path which satisfies this condition is called the classical path, okay, because that is what sticks out and that is how classical mechanics comes about. Classical mechanics from the Lagrangian will give you this equation, etc., etc. So, you can compute the action for a classical path, but now it will be a function of the endpoints, because the action depends on x1 t1 and x2 t2, even though I did not write it down explicitly. So, you stick it here the classical path, you evaluate this integral, then it is just a function of the endpoints. Then you want to know how this action changes when I change the endpoints. Okay. So, when you do that, first we already have one result. If this quantity is 0, then I know that delta A is just going to be p times delta x at the endpoints. So, let us assume that the first point is kept fixed and at the upper point I am changing x, and instead of x2 let me just call it x. Then I get the result that dA by dx, this delta x go and sit below that delta A, this is p. So, make sure you understand this relation. This arises when A is not treated as a functional here, A is treated purely as a function of the endpoints when that A is computed along the classical path. So, if you calculate the A along the classical path, to be very precise I can even put a C here. So, the classical path is xc and the value of the action as evaluated for the classical path is the classical action, which is AC, and that depends on the endpoints, and when you do this, this is what you will get. Okay. So, what about the time derivative? What is dA by dt? Okay. So, in order to do dA by dt, there are, let me rub this out. You just need to do a little bit more work. To do that, you start with this relation, total derivative dA by dt is by definition the Lagrangian L. Okay. You think of it as the partial derivative dA by dt, because it depends on the endpoints both this and dA by dx into x dot. It is just the rule of partial derivatives, that is the total derivative is partial ordinary derivative plus A depends on x and x depends on t. So, you get this. So, this dA by dx we already evaluated, that is equal to p. So, there is a p times x dot. So, you find that this dA by dt is L minus p x dot. People usually write it as minus dA by dt. So, dA by dt would have been L minus this quantity. So, this is p x dot minus L. Okay. Now, what is this quantity? Let us again evaluate it. So, if you take for example, the particle in with a kinetic energy and potential energy, then p x dot, what will that be? P is m times x dot. So, this will be m x dot square, mv square. Then when you subtract a Lagrangian, half mv square will go away and you will get half mv square. Then there is a minus potential energy in Lagrangian which will become plus potential energy. So, the total thing is like an energy functional. Okay. So, you can think of this as energy functional E, and it is given as a function of x and x dot. So, it is half mv square plus u, half mv square depends on x dot and u depends on x. Now, of course, because this quantity gives you p, or even this relation gives you p as a function of x dot, I can translate this back and write x dot in terms of p. So, I can express the same quantity in terms of p and x. If you do that, it is called a Hamiltonian. Okay. So, the difference between Hamiltonian and the energy function, this is again a hair splitting distinction, but sometimes it is useful to have that, is that both of them are numerically the same. If one gives 5 electron volt, the other will also give 5 electron volt. But the energy function is defined as a function of x and x dot. Hamiltonian is defined as a function of p and x dot. Okay. So, you can also have a definition of the Hamiltonian, which is numerically the same as this, but I will denote that it is a function of p and x, which is p x dot minus L. So, at this stage it might look as though this is all trivial and I am redoing classical mechanics, but just as an example, let us take the free particle, which is supposed to be completely trivial, for which we have the action here. Okay, and let me just concentrate on the action, which is this. So, the Lagrangian for a free particle, now I am not taking any weak field or any approximation, this is the fully relativistic particle, is minus mc square into 1 minus v square by c square to the power half. So, at this stage there is one comment which I wanted to make, because you will read a wrong statement in several textbooks, even some good textbooks. So, it is a good idea to correct this. So, suppose you take this Lagrangian and you take c going to infinity limit of it. What will you get? You will get a half here. So, you will find that in the c going to infinity limit you get minus mc square plus half mv square. So, the textbook statement is that in the non-relativistic limit, when you take c going to infinity, this Lagrangian reduces to the standard Lagrangian, which is the kinetic energy. This standard statement is completely wrong. It does not reduce to it. This function actually has no c going to infinity limit, because when you take c going to infinity, the first term blows up. Okay? So, this function simply does not have that limit, and in fact, it is a general theorem that you cannot write down any Lagrangian which depends on c, such that when c goes to infinity, it gives you half mv square, and also it is consistent with special relativity. Okay. So, that statement that you can get non-relativistic mechanics by an approximation is not true. The usual way people try to cheat there is that they will first say, look, I can always add a constant to the Lagrangian as far as I am doing classical physics. That is true, because the Lagrangian only cares when you are doing the variation, you have only derivatives. So, the Lagrangian only cares about the non-constant factors. In fact, something more general can be said. I can always add to a Lagrangian a total time derivative. That is, suppose I change L to L plus d by dt of some function of t and x, not x dot, only t and x. Okay. What will happen is that if I do an integral over dt, this function is going to contribute only at the endpoints. At the endpoints, it is fixed. Therefore, when I vary the path, this f will keep giving me the same value. So, under the variation, they will go away. The same equation of motion which we wrote down and rubbed off, I mean this is equal to 0, that equation of motion will hold for both these Lagrangian. So, you can even add a total time derivative of a function, which we will use in later lectures, to a Lagrangian, and nothing will change. Nothing will change meaning in the classical dynamical equations will not change. So, you can say that, oh, you take this Lagrangian and add to it mc square. Instead of this Lagrangian, take this Lagrangian from mc square plus mc square. Okay? Then of course, when you take the limit, that m minus mc square cancels with plus, and you get half mv square. So, everything is nice. No, everything is not nice. The point is that when you add a plus mc square here, this quantity integrated over dt, remember where it came from? It came from this ds. Okay? Now, you are going to pick up an extra term, you will get ds, and you will pick up an extra term which is mc square dt. Now, the mc square is a constant, but dt is the time interval. Time interval changes when you go from one Lorentz prime to the another. So, your action is not going to be Lorentz invariant, that is not consistent with special relativity. in a formal sense. Of course, you can take the point of view that I only care whether my equations of motion are relativistically invariant, I do not care about the action, but that is not such a nice argument. You would like to have formal invariance of the action. The action which is built out of ds as we did is completely Lorentz invariant, and this particular quantity is something which does not change when you make a Lorentz transformation. If you do not know that result, you should just go back, write down the Lorentz transformation, take dt and dx of that and compute this quantity. You will find that it is invariant. Okay. So, to begin with, this statement that this gives you non-relativistic limit correctly is to be taken with a pinch of salt. So, since you will not see it in the textbooks and you will often see the wrong statement in the textbook, I thought I will spend a moment on that. But let us go ahead with this. Yeah.
So what if we say the velocity is very low?
Oh, then it is fine. If velocity is very low, this half mv square is correct. But even then you have an mc square. So, you are throwing away the dominant term which is mc square and you are retaining mv square. I mean, no mathematician will agree with that. So, the formal statement is that this function does not have a c going to infinity limit. It blows up when c goes to infinity. Okay. Right. Now, let us redo this, redo exactly what we have done. Okay. So, that is why I wanted to do this, because this again works for any system known to physics. Similar ideas work for electromagnetic field. You will find that if you think of x as electric field, you will get p as the x as magnetic field, you will get p as the electric field. Okay. So, what is the dynamical variable etc. is a very general statement. So, let us see what happens in this case. So, here if you compute p, which is dl with respect to dx dot, which is dl with respect to dv. So, what you will find, you can do the algebra, you will find that this is mv divided by root of 1 minus v square by c square. Okay. Now, again this is a good time to correct if somebody has told you at some stage, God forbid, that mass increases with velocity. Mass do not increase with velocity. Mass is always a constant, it is m. Okay. Now, that comes historically because people saw this relation and they said, oh, we want it to be mass times velocity, therefore, let us assume mass changes with velocity. That is complete nonsense, because if you write down the corresponding expression for energy which you can get from this, so you should go and work it out. So, you take this p multiply by v, that will be mv square upon this, and subtract the Lagrangian. You will find that the energy is given by energy or the Hamiltonian, but energy, because we are writing it in terms of v, is given by mc square upon root of 1 minus v square by c square. If you wanted this to be mv and you define m by this, instead I could have said I want energy to be half mv square, and I could have said that m has to change in a particular way to do that. These two are not consistent, and in fact one of them will give you nonsense. Okay. So, the easiest way to think about this is that all these quantities like momentum, energy, etc. are defined by these relations, this relation and this relation. You give me the Lagrangian, I will give you what is the momentum, what is the energy. Okay. Do not imagine that it should be like m times mass times velocity, mass times v square, etc. Those are special cases, but these are the most general expressions which we know. So, you have got these two. Now, what you can do is that you can go and substitute for v in terms of p, that is you can solve for p square in terms of v square and plug it into this. Then you can express energy as a function of momentum, right, and that is how you want to define your Hamiltonian. So, if you do that in this particular case, you will find that the Hamiltonian satisfies the relation. These are left as an exercise if you have not done it in special relativity. Okay. So, Hamiltonian will be the square root of that, but the square of the Hamiltonian is p square c square plus m square c to the power 4. Okay. This is the relativistic relation, and this reduces to again p square by 2m plus mc square. This will give you an approximate form for H as p square by 2m, which is what you have in non-relativistic physics, plus mc square, which is called the rest energy in the approximate limit. So, all these things which we know in special relativity, etc., everything comes out of one assumption, that the action for a particle is length of the path. Okay, that is all we did. We didn't introduce any other assumption. Rest of it is all definitions, and with these definitions you can get all these results. So, incidentally this also tells you something very nice which we do not have time to go into now, but we will do it in the end when we do electromagnetic field. If you have been looking at expressions like this, it does not have a natural m going to 0 limit. If you put m is equal to 0, it vanishes. If you put m is equal to 0, this vanishes. But at this level, once you have brought it down to Hamiltonian, if you put m is equal to 0, you get h is equal to Pc. Okay? So, you can have particles with 0 mass, but it can have a momentum and energy which are related by h is equal to Pc. You remember when we did electromagnetic radiation, we did not call it radiation, but when the electromagnetic potential, vector potential I wrote down the wave equation for that, and then we did a Fourier transform, we got a relation that the frequency of the harmonic oscillator is k square times c square. We derived it in the first lecture. Okay? I showed that the electromagnetic field is a bunch of oscillators. The frequency is labeled by the wave vector k and it is given by this. So, this is what I would have got, and if we following Planck put a h cross here and a h cross here, then what you find is that h cross omega, which is the energy, is equal to c times h cross k, which is the momentum. Okay. So, the harmonic oscillator quanta which we found in when we did the dynamical variables of our electromagnetism actually satisfies this. That is why we say that those quanta which are photons have 0 mass. So, relativity adds this extra bit, which as I said you cannot derive from this because that limit does not exist, but once you have come up to this, the existence of 0 mass particles is possible in relativity, which you cannot do in non-relativistic physics. Okay? So, we have now done the action principle and the various definitions of the action principle and how it ties in with this. And in the next lecture, we will use these results to obtain an equation satisfied by this wave function. Or rather, we will determine the equation satisfied by G. That will also tell us what are the conditions on the summation over paths and what paths we can sum, etc., etc. That is what we will do in the next lecture. Questions, comments? We will stop there. Yeah.
You were starting, you were saying that we are in classical limits.
Right.
So
There is a classical limit to find all these things. Yeah, right.
where did the idea of space-time come in classical limits?
Oh, classical limit as space-time. You are confusing non-relativistic limit with classical limit. You have quantum mechanics, and when you take h cross going to 0, you get classical limit. You can get a classical limit which is fully relativistic. General relativity is a classical theory. The word classical is non-quantum. Okay? So, when I say classical limit, it is a non-quantum theory. It is a non-quantum limit. That is the h cross going to 0 limit. The special relativity etc. exists as long as c is finite. Then if I further take c going to infinity, I get non-relativistic limit. So, I am not talking about non-relativistic limit, I am talking about non-quantum limit. So, do not think of classical as non-relativistic. Yeah.
Here, this ds square is equal to minus c square dt square
Right.
dx square comes from
Special relativity.
special relativity, means we assume that speed of light is constant.
No, you do not assume that. In fact, that depends on how you have been taught special relativity. If there are some basic postulates, there is a various kinds of postulates which you can think of. The minimum thing which you need is that you say that the speed of light is not the same, is the same for all inertial observers. And then from that, with some thought experiments, you can show that there is some way in which space and time has to change, and then this is the quantity which will remain invariant.
Is there a way by which we can show this statement, means the fundamental postulate, the light is constant for every frame?
No, no. There is no way you can prove that for light the speed should be invariant under all inertial observers. That is an experimental fact which is used as a postulate. Of course, you can trade that for some other postulate. If you assume, for example, Maxwell's equations are correct, then you can show that the Maxwell's equations remain valid in all inertial frames. and in all inertial frames the waves of the Maxwell's equation propagate with the same speed. Okay. So, you have to make some postulate somewhere, and it is simplest to say that speed of light is independent of the motion of the source or the observer.
Means we have to take it as granted. We can't start with.
You cannot establish it from something more fundamental, no. Any other question? Yeah.
What I wanted to ask at that time was that the space-time element which you have got for weak field limit,
Right.
it's not the full source side.
That is correct.
So what actually we
Okay. So, you are asking not so much as where I took the space weak field limit, the question is why is that 1 plus 2 phi by c square dt square etc. Okay. There are two ways of answering it. One is that as far as our purpose goes, I can only handle weak fields because I am going from special relativity to general relativistic corrections, and that is always a local effect. When the curvature effects really become dominant, that analysis does not hold. I mean, I can't have two lifts or two clocks next to next if the curvature scale is large. Therefore, I have to assume this, and what I have obtained can only be valid in the weak field limit. Now, in the actual strong field limit of gravity, if you start with Einstein's equation in strong field limit, then you can solve Einstein's equations taking phi by c square is small. Okay. So, that is the approximation you use. This phi by c square you assume is small. Then when you solve, you will find that the one metric coefficient, the one which multiplies dt square remains non-trivial, and dx square, dy square, dz square become unity in that limit, and that is how you get that.
basically the way you used the equivalence principle.
That is right. The way I have used equivalent principle, it is valid only locally, therefore, I cannot get the full gravity out of that. Yeah. There, right.
Is there any interpretation of that minus mc square, that extra term which is in the
Okay, it is the only way you can interpret. Okay, there is a very complicated interpretation of time lapse over a closed loop, etc., which is there in one of my technical papers. So, if you are interested, you send me an email and I will send you the reference. But the simplest explanation is that when you take this expression for energy, for example, even a zero velocity body has a energy mc square. So, when you do the Hamiltonian, that fact has to go in. So, if the Lagrangian has an additive constant, like if you think of it as half mv square minus mc square, it is like adding an energy mc square to the Hamiltonian. Okay. So, what you subtract from Lagrangian gets added to the Hamiltonian, because Hamiltonian is p x dot minus L. So, there is a, if you say that there is a rest energy, is the simplest explanation is a rest energy. Yeah. There was some other hand up here. Yeah, right.
In calculating the propagator,
Hmm.
do we have to take the paths that lie outside the light?
That is a good question. That is going to come up in next lecture. But just to give you a glimpse of what is there, I told you that this is what we are going to do, and the action is given by this for any path x dot, right. I mean, you give me a path and I compute x dot and I do this. But nobody told me that my x dot should be such that x dot square by c square should be less than 1. So, I can have paths which are where this is larger. If it is larger, the square root is going to become imaginary, and when I am going to write e to the I times that action, that is going to give me an exponential damping. Okay. So, those paths are suppressed, and it is like tunneling which happens in quantum mechanics. So, we will discuss this in greater detail in the next lecture, where what kinds of path has to be summed. So, in non-relativistic limit, you choose paths in such a way that such problems do not arise. Okay. So, that is an extra postulate, but in principle this can happen. Yeah.
So here we are assuming that each event is independent along the path. Each event is independent of the previous event, right? So we just multiply the amplitudes.
No, not event is not independent. You are saying that the amplitude for the particle to go along this path can be thought of as the amplitude for it to cover a small distance, then an amplitude to travel another distance, etc.
So we say that these
Right. These amplitudes are independent.
but
Yeah.
can there be any case where you need to apply Bayes rule, where the amplitude depends on
No, not really, not at an infinitesimal limit, because whatever correlation comes up will be higher order. But of course, each element can be weighted differently. That is exactly what happens when you do this. So, you take a small element dx that is multiplied by a vector a, which can depend on x, the position. So, when you take the next dx, your a will be different. So, you are weighing each element by a different A, and that is what electromagnetism does. Okay. Yeah.
You were talking that this amplitude is we are multiplicating.
Correct.
Why is not additive?
Why is probability is not additive? If we have, it is the same reason, that is if you have two events which are independent, then you multiply the probabilities. It is the same reason we are doing it with an amplitude.
Can you elaborate just what do you mean by amplitude of path?
That we did in the previous lecture, that is if you take a two-slit experiment, then if you want to get that interference, it is not enough that we have probabilities. It is not enough that we say the probability for a particle to go on one path is P1 and another path is P2. We actually need these probabilities to cancel each other. Probabilities do not cancel because they are positive definite. So, you need to introduce an amplitude, and that amplitude is defined in such a way that the mode square of this is the probability. It is a complex number whose modulus square gives you the probability. Okay, we will meet on Friday. Thanks.